So when we talked about the convergence of martingales, we first started with the simple almost sure convergence. Then we looked a bit into the convergence in L1 by looking at uniform integrability. And now what we're going to do is to look into the convergence on Lp of martingales. So Lp convergence, but first we have to give Lp bounds. On martingales. To be able to give results about their convergence, we need first to talk about their moments. And more precisely, we have to talk about the moments of the maximum of a martingale. So this is going to be the main content of this lecture. So we again have a submartingale. And we fix some p between 1 and infinity. That's going to be the p that we talk about in this Lp convergence later. But for now, what we're going to do is not concerning convergence, but it's going to be important for convergence later. It's only going to be a bound on the mn, which if you recall well, it's the maximum for I smaller or equal than n of xn. We're going to bound the expectation of mn to the power p. So we have a submartingale. We know that the maximum in certain ways behaves like the last point. And what we're going to show is something in this direction, but concerning the pth moment of the martingale. And it's going to be a bound of the following form. It's p over p minus 1 to the power p, expectation of the positive part of xn to the power p. So this is looks a bit weird at first, but again, it's another of these theorems that relate the maximum of a process with the last point of the process, but you do have to take the pth power here and multiply by this strange factor in front. So, sorry, here we are going to talk about the maximum positive part. So, this sometimes is called x star n. But let's keep the maybe m star, I don't know, m bar. Just to remember that it's the positive part that we're talking about here. So the positive part is here and also in the end. The pth power is the same, and we get this strange factor here. So again, we are relating the maximum with the last point, but now in terms of the pth moment. Okay, so before we go to the proof of this theorem, an interesting corollary is in case we have a pure martingale, not a submartingale, then the absolute value of yn is a submartingale, because the absolute value is a convex function. It's not increasing, but we don't need increasing if we start from a martingale. So that means that the maximum for I smaller or equal than n of yn absolute value let's call this y star n, satisfies a moment bound. So we take y n star to the p. In expectation, it's bounded by the same factor, p over p minus 1 to the p times the expectation of yn to the p. Why is this corollary true? This is exactly the process m bar because y is already non-negative. So taking the positive part doesn't change anything. So this is already the process m bar associated to these random variables here. So this is a nice corollary where the positive parts don't play any role. Oh, sorry, here there's an extra parenthesis, or maybe the p should be inside here. Yeah. So again, it's a bound on the moments. So now let's go to the proof of the main theorem. The proof of the main theorem is not especially complicated. It has two ingredients, or maybe three ingredients. First, we have to regularize the process X because we're gonna take expectations of things and we want to limit these things, and then we take the regularization to infinity. So the way we're going to regularize this is by taking xn and we're going to take the m n bar, this maximum, and we're going to saturate it up to some constant k. So we don't know if this variable is integrable or not, but this variable is bounded, so it definitely can integrate this variable. So this is the first step. Another important step is Doob's inequality. We are going to see why. And the third important step, I don't know if you remember this from probability 1, but in probability 1, we first saw that if random variable w is bigger or equal to 0, then its expectation can be written as the integral from 0 to infinity of the probability that w is larger or equal to t dt. I don't know if you remember this, but this is an important theorem that you can easily prove by writing w as the integral from 0 to w of dt and using the Fubini's theorem. Okay, this same proof and the same result has an analog for the pth moment, and it's something you should remember because it's useful several times. The expectation of w to the p can also be written as an infinite integral, but now of p t to the p minus 1. You see that here we are just writing the the derivative of t to the p, and here there was a derivative of t to the 1. So this is the derivative of t to the p times the probability that w is larger or equal to t dt. Why the derivative appears here? It has to do again with the same way to write this as an integral, the integral of the derivative, and then using Fubini. So you're going to join these three ingredients and the proof is going to follow very easily. So you see, let's just connect the dots here. You see that Doob's inequality is very good to bound things like this, right? And we in the end are trying to estimate an exponential moment, a moment of order p like this. So we're gonna be able to use Doob's inequality when we get to that point. Okay, now let's go indeed to the proof. So as I said, we start taking the M process, M bar. Let's recall what it is. This is the maximum for I smaller or equal to n of xi positive part. And this process, we're gonna limit it with k. So instead of taking the moment of mn to the p, we're gonna limit at k. And why it's gonna become clear? First of all, because we didn't even know if this process m bar had a p moment. But now it's bounded, so it does have a p moment. And by using the inequality that I wrote here above, we know that this is equal to the integral from 0 to infinity of p times t to the p minus 1 probability that mn infimum k is larger or equal than lambda, larger or equal than t dt. Okay, m bar. We would like to use Doob's inequality here, but the fact that we bounded the m bar by k is giving us some problems, because in Doob's inequality we can estimate a probability of the type m bar n larger or equal to t, not this. So there is a problem here that we have to solve. So the way we solve this is by looking at this event and studying what can happen with this event. So there are two cases. M bar infimum k larger or equal to t can be two things. First, if k is larger or equal to t, let's look first at the other case. If k is smaller than t, the minimum is also smaller than t. So there is no chance that the minimum is going to be larger or equal to t. So this is exactly the empty event. If on the other hand, k is larger or equal to t, then what counts is really m bar. Because if m bar is also larger or equal to t, the minimum is larger or equal. If m bar is strictly smaller than t, the minimum is strictly smaller than t. So this event is only going to look at m bar, which is great news because Doob's inequality works for this event. So now let's rewrite what we have and see if you agree. So here we have p, t to the p minus 1. I'm going to write what I want to have in the end, and you tell me if you agree. I want to have mn bar larger or equal to t dt. So let us look at the possibilities. So k and t are deterministic points. When we look at this probability, they are just numbers. So if they are such that the event is empty, then this probability is 0, which is smaller or equal than this probability. Or this is exactly this, then it's smaller or equal than this. So in any case, I can bound the above integral by the integral below. And now we are in a good position to use Doob's inequality. So this is going to give us the same integral, but with the 1 over t. So in Doob's inequality, the t is multiplying here. times the expectation of x plus at the last time indicator that x and indicator that m and bar is larger or equal to t. Now dt. Okay, here there is an important observation. Here we have the event m larger or equal to t. And I'm going to repeat the same argument as we did here, because I want to put the minimum k here again. So why can I do this? Let's just first do it, and then we argue. Okay, I want to put here, I want to put minimum k here. Let us see why I can do this. So again, when we are looking at this this event here, either this event is let me write here below, without the minimum. That's what we get by Doob's inequality. So if k and t, so you see that the integral, we didn't touch the integral. We are doing these inequalities by looking at only what is inside the integral, point by point. So if t and k are such that this is empty, so this is 0 and this is smaller than this. Now, if k and t are like this, so that we can replace this event by this, we can do the replacement until we reach here, and then we can do the replacement again. So it's not true that I can go over all these steps like I did, but it is true that this integral is smaller or equal than this integral, because I can separate into k smaller than t and k bigger than t. So now we have what I want. Why are we so close to finishing? Now I can really do some simple evaluations here. So we have a t to the 1 minus p minus 1 here. So we can get, I'm actually gonna already use Fubini here and interchange this expectation with the integral. It's gonna make my life easier. This random variable has no t on it, so it goes out of the integral. And here, I'll first write the integral from 0 to infinity. P t to the p minus 2 minus 1 here from another one here. And then we get the indicator function. And I'll rewrite it as t smaller or equal than m n bar minimum k. dt, end of expectation. Now let's copy this to the next page. And see, oh, some stuff didn't come. The parentheses, I think that's all, yeah. So this integral is actually the integral from 0 to m n bar infimum k of p t to the p minus 2 dt. You see, if I'm taking the indicator function that t is smaller than something, this something becomes the upper limit of the integral. And now this is a simple integral from calculus and gives us, I'll repeat, expectation of x n plus, and here we get p that goes out of the integral, mn bar k to the p minus 1 over p minus 1. So now what we have is something that looks like what we want, but there is one point here to mention. You got the xn, but we're still taking the expectation of a product, and we don't know much about the expectation of products, except that we can use Holder's inequality. So we can choose P. We actually have something that looks like a good candidate for P moments here. So we're going to take Q, which is P over P minus 1, which is the dual of P. So we can first remove this P over P minus 1 outside here. It's a Q, right? And then we have an expectation of a simple product, and we can use Holder's inequality to get xn plus to the p to the 1 over p, and this to the p minus 1 to the q to the 1 over q. And let's rewrite this. So this is just the same. And the second one, we have p minus 1 times p over p minus 1. This is just going to give us p. And here on the outside, we have 1 over this. So this is p minus 1 over p. Okay, what's interesting, let's recall what we have here. We proved that several things are chained together, but we started with the expectation of m n bar minimum k to the p. So now we reached the same expectation again. So we can send this to the other side. It's a positive thing. So we're going to get the expectation of m n bar minimum k to the p to the power 1 minus p minus 1 over p is smaller or equal than q, the expectation of xn plus. By the way, if it's plus, we don't need this, right? To the power p to the power 1 over p. And what is 1 minus p minus 1? This is p minus 1. This is going to be 1 over p. Now I'm going to replace q by what it is. And here we're going to take everything to the power p. So we get the expectation of m n bar minimum k to the p is more or equal than p over p minus 1 to the p, expectation of x n plus to the p, and that's it. So now you see that we got rid of the dependence on k in the right hand side. So the right doesn't have any k. So now finally we can take the limit as k goes to infinity, and we get that these expectations, this is a dominated, monotone convergence to the mk, and you get the expectation of m n bar to the p is bounded by the same thing. So this was a bit of a long proof, but it's in the heart, it's just this inequality here applied to our maximum, but truncated with k. And then we also use Doob's inequality when we reach this probability here. Okay, so this was LP bounds on martingales. And the next class, we're gonna use those bounds to prove an LP convergence theorem for martingales. So see you next class.